All right, let's talk about recursion in game development. Now, I know it can sound a little intimidating, but trust me, it's like a secret weapon. It's the magic behind some of the most complex and, honestly, most elegant features you see in games.
So have you ever been playing a game and just wondered, how does it do that? How does a chess AI seem to know exactly what you're going to do next? Or how can a game generate a whole universe of unique planets? Well, the answer, a lot of the time, is recursion. And today, we're going to break down exactly how it works.
Okay, so what is recursion really? In the simplest terms, it's just a programming method where a function calls itself. The whole idea is to take a huge, complicated problem and just chop it down into smaller, bite-sized, identical pieces. The Russian nesting doll analogy is honestly perfect for this. You pop open one doll, and what's inside? A smaller version of the exact same doll. And you keep doing that until you get to that last, tiny little doll that you can't open anymore. That final doll, that's your solution. That's what we call the base case.
Right, so let's get into how this actually works. Because for this to be a useful tool and not just, a way to instantly crash your game, a recursive function has to follow two super strict rules. It's all about this delicate balance between repeating a process and knowing exactly when to hit the brakes.
So, here they are. Rule number 1, you absolutely have to have a base case. Think of this as the emergency brake, the stop sign. It's the condition that tells the function, okay, you're done, stop calling yourself. Without this, you get an infinite loop and, yeah, that's bad. Then you've got the recursive case. This is the part of the function that does the work and then calls itself again. But, and this is key, it does so in a way that gets it one step closer to hitting that base case.
Okay, that's enough theory for now. Let's get to the fun part and see how this actually shows up in gameplay and the features we all know and love.
We're going to look at 3 really common use cases. We'll start with how it's used to navigate game trees for things like chess AI. Then we'll jump into procedural content generation. Think Terraria or No Man's Sky. And finally, we'll touch on how it simplifies complex collision detection.
So first up, navigating game trees. When you're playing a strategy game like chess and the AI just feels impossibly smart? That's because it's seeing into the future. It isn't just looking at its next best move, it's looking at your best response to that move, and then its response to that, and so on. All these branching possibilities create something we call a game tree.
And this is where recursion is just perfect. An algorithm like Minimax will basically travel down every single branch of that game tree. For each potential move, a function calls itself to figure out the opponent's best countermove. And for that countermove, guess what? It calls itself again, digging deeper and deeper. It only stops when it hits a base case, which could be something like a checkmate, or maybe it just reaches the limit of how many moves ahead it's allowed to think. Okay, next up, procedural content generation. This is how you get those absolutely massive game worlds. I mean, can you imagine a designer having to hand place every single tree, every single mountain? No way. Instead, developers can write one smart function that generates a little piece of the world and then tells its neighbors to do the exact same thing. Imagine a function called, say, generate terrain. Its job is to create one single tile of grass. But it doesn't stop there. Once it's done, it calls itself for the tile to its right and the tile above it, and so on. Each of those new calls does the same thing, and it just spreads outward like a ripple in a pond. Before you know it, you've filled an entire map based on a set of rules. It's just an unbelievably efficient way to create these huge, diverse landscapes.
All right, use case number 3, collision detection. Now, physics can get messy. Imagine your character is standing on a platform, which is inside a moving truck, which is on a moving ship. Checking for collisions across all those nested layers gets really complicated, really fast. But Recursion, it handles this beautifully.
So here's how it would work. You'd have a function, let's call it check collision, that checks for a hit on the most immediate layer. If it finds something, awesome, it reports back true and we're done. But if there's nothing there, its recursive case is to just call itself on the next layer down in the hierarchy. It just keeps digging down layer by layer until it either finds a collision or it runs out of layers to check. And that's its base case. Okay, so now we're moving into the pro-level stuff, optimizing for performance. Because let's be honest, we have to address the elephant in the room here. A lot of developers are, kind of taught to be a little scared of recursion. Because if you're not careful, it can be a real hog on system resources.
And look, that's a totally fair question. Isn't recursion inefficient and a drain on memory? Well, yeah, it can be. See, every single time a function calls itself, it adds another layer to what's called the call stack in your computer's memory.
If that stack gets too deep, you can run into some major performance problems. But thankfully, there are some pro-level techniques to get around this.
So optimization number 1 is something called memoization. It sounds like a super fancy word, but the idea behind it is actually really simple. Don't solve the same problem twice. That's it. When your function figures out an expensive result, it just saves it or caches it. Then, if it ever gets asked to figure out the exact same thing again, it doesn't have to do all the work. It just grabs the answer from the cache.
The textbook example for this is calculating Fibonacci numbers, where you end up recalculating the same small values over and over and over again. By storing those results, memoization can turn a function that's painfully slow into one that's lightning fast. And in a game, let me tell you, that can be the difference between a super smooth AI and a massive game-breaking lag spike.
Okay, optimization number 2 is tail recursion. Now this one's a little more technical, but it's a special situation where the recursive call is the very last thing a function does before it finishes. When that happens, some smart compilers can perform a neat trick. Instead of adding a whole new layer to the memory stack, they just reuse the current one. This basically turns the recursion into a super efficient loop, which is a great way to prevent those nasty stack overflow errors.
So now that we've got all that, how should you actually use recursion in your own projects? Let's wrap things up by boiling this all down to a few key best practices you should always keep in mind.
All right, first up, know when to use it and when not to. For problems that are naturally recursive, like navigating a tree, it's incredibly elegant. But for something simple like a countdown, just use a regular loop. It's usually clearer and more efficient. Second, keep your recursive functions small and focused. Have them do one thing and one thing only. It'll make your life so much easier when it's time to debug. And finally, always be mindful of how deep your recursion might go. If you think a function might need to call itself thousands of times, you should probably look for a different solution to avoid crashing with a Stack Overflow error.
Look, at the end of the day, recursion isn't something you should be afraid of. It really is an invaluable tool. Once you get the hang of it, you unlock this amazing ability to solve really complex problems with code that is surprisingly clean and simple. And that is how you create more dynamic, more engaging experiences for your players.
So I'll leave you with this question to chew on for your own projects. Think about that one problem you're stuck on, the one that seems impossibly complex. Could it be pathfinding, AI, maybe world generation? Is it possible that the elegant answer you're looking for is actually a recursive solution? Something to think about. Happy coding!